Hello students, this video is about a series LCR circuit. That means we have a circuit that contains a resistance, a capacitor and an inductor connected in series to an EMF source having alternating EMF equals epsilon naught sine omega t. So before starting that, first of all we will draw a diagram for that. So here, as we can see in the diagram, resistance R, inductor of inductance L and capacitor with capacitance capital C are connected in series to an alternating EMF source of EMF epsilon is equal to epsilon naught sine omega t. So we have here the alternating EMF source of EMF epsilon naught sine omega t, and we are assuming that capital I be the current in this series circuit at any instant. So what we are assuming that at any instant capital I is the current in this series circuit. Then we have three circuit elements, so we have to check the phase relationship between their voltages and current separately. So first of all, for resistance the voltage VR vector, the phasor for VR is equal to RI vector. That means the phasor of VR is equal to R phasor of I across the resistance capital R, and in this case this VR vector will be in phase with the current. So this voltage will be in phase, that means in same direction with current. So in diagram we have to show like this, that if this is the direction of current, then voltage is in the same direction. Now this time we are talking about the voltage VR only, not about the inductor and capacitor. So VR and I are in the same direction, and its amplitude of the phasor VR is, the maximum value of it is V naught R is equal to I naught R. This is for resistance. Now moving to the second circuit element, that is inductor. For inductor, voltage is VL vector is equal to XL, the reactance of inductor, and I vector. This is across the inductor, and this voltage is ahead of current in phase by pi by 2 radians. Okay, so for inductor voltage is ahead by pi by 2. That means if this is the direction of current, then voltage is pi by 2 ahead, voltage is leading, this is pi by 2, and this is the direction for voltage. In case of inductor, this voltage is VL, means voltage for inductor. So for inductor the voltage is ahead the current in phase by pi by 2, and its amplitude of VL vector is V naught L is equal to XL I naught. This is for the peak value or the amplitude of the voltage VL. Moving to the third circuit element. The third circuit element we have is capacitor, and the voltage VC vector is equal to XCI vector across the capacitance. This is the voltage across the capacitance, and this voltage lags behind the current in phase by pi by 2 radians. So for inductor voltage was leading by pi by 2, for capacitor voltage is lagging behind the current by phase pi by 2. So we can plot it like if this is the direction of current, then voltage is pi by 2 lagging. This voltage is Vc, this is pi by 2, this angle is pi by 2, and voltage is lagging the current by pi by 2 radians. And now come to its peak value or the amplitude. Amplitude for this voltage Vc vector is V naught C is equal to Xc I naught. V naught C is equal to Xc I naught. These are the values for all the peak values for V naught R, for VR, for VL and for VC, and we have studied the phase relationship separately. Now we have to see this for whole circuit. Means we want to find the resultant EMF epsilon. For that we have to find the resultant of VL, VC and VR. So first of all we are going to form a phasor diagram for all these three. Let's see how we get it. So for phasor diagram, first of all we are plotting current and VR, and they both are in same direction, are in same phase, so they are plotted along the same line. So here on the diagram I have plotted phasors for VR vector and I vector. These are along the same line because voltage across the resistance and current are in same phase or in same direction. So this is for resistance. Now we have to plot for inductor and capacitor. We know that the voltage of inductor, voltage across the inductor is ahead of current by pi by 2, means for that we have to move pi by 2 anti-clockwise, and for capacitor the voltage lags behind the current by pi by 2, means for capacitor we have to move pi by 2 clockwise. Okay, so the lines or the phases that we get are like this. This is for capacitor, that is lagging behind the current by pi by 2, and this is for inductor, that is leading the current by pi by 2, and these angles are pi by 2 radian and pi by 2 radian. But now this diagram I have made is for the condition that VL is greater than VC. I make this phasor longer in comparison to this one. So VL is greater than VC. If there is a condition like VL less than VC, that is also possible. In that case the phasor for VC will be longer and VL is smaller. Then if I find the resultant of VL and VC in this diagram, I will find the resultant in the direction of VL, and it will be VL minus VC and in the direction of VL. This is because VL is greater than VC. So to find the resultant EMF epsilon, we have to find the resultant of these three voltages. First of all we have to take the resultant of the two, then with the resultant of these two VL and VC, that voltage and voltage VR will give us the final net EMF epsilon. So if VL is greater than VC, in that case the resultant of these two is VL minus VC and in the direction of VL. But if VC is greater than VL, then it will be VC minus VL and in the direction of VC. So this we have to remember. That diagram we will also plot after this one. First we are going with VL greater than VC. Now we want to find the resultant of VL minus VC vector and VR vector. For this we are going to use parallelogram law of vector addition. So by using parallelogram law of vector addition for the vector VL vector minus VC vector and VR vector, the diagonal give us the resultant EMF epsilon vector, and this epsilon makes angle omega t with axis and phi with current. Okay, so the resultant makes angle omega t because it is epsilon naught sine omega t from the axis, and phi, we are assuming that it is making the angle phi with the phasor of current. So now we have to find the magnitude of epsilon and its direction, that is phi. For the magnitude of epsilon, we have to find the resultant of the two vectors, that is VL minus VC vector and VR vector. So we can write epsilon vector as VR vector plus VL minus VC, these vectors. Now this is for VL greater than VC. If VC greater than VL hota, then it will be VR vector plus VC minus VL vector. Now for magnitude, epsilon naught is equal to under root V naught R square, that is the magnitude of VR, and plus V naught L minus V naught C square plus 2 V naught R V naught L minus V naught C cos angle between the two is pi by 2. So this term will be 0 because cos 90 is 0, and we get epsilon naught is equal to under root V naught R square plus V naught L minus V naught C square. By substituting the values in terms of current, we get epsilon naught is equal to under root, now V naught R is I naught R square, and V naught L and V naught C are I naught XL minus I naught XC whole square. So epsilon naught is equal to I naught under root R square plus XL minus XC का whole square, which implies the current I naught is epsilon naught upon under root R square plus XL minus XC का whole square. Now from this equation we can conclude that the denominator works as an effective resistance, so we call it as impedance. So the opposition that is offered by the LCR circuit in the flow of AC is the impedance Z, which is equal to under root R square plus XL minus XC का whole square. If we substitute the values of XL and XC, then we get it is under root R square plus omega L minus 1 upon omega C का whole square. This is the impedance. Its SI unit is ohms because it's the opposition only, and this shows the relationship between the resistance, inductive reactance and capacitive reactance for the circuit. Now we can also show this relation by a triangle, since it acts like a Pythagoras theorem. If we write it as Z square is equal to R square plus XL minus XC का whole square, so we can form a right angle triangle for this. If we form a right angle triangle for this, then the sides of this triangle are XL minus XC and the hypotenuse is Z. This is a right angle triangle, and this angle that Z or the effective resistance make with R, with the direction of R is phi, because the direction of resistance and voltage across resistance and current is same. So this triangle we call as impedance triangle. This impedance triangle shows the relationship between resistance and inductive reactance and capacitive reactance. We call it as impedance triangle. Now for the direction of epsilon, means for the value phi. To find the value phi, we have to find tan phi, and tan phi is perpendicular upon base, and this distance is equal to the magnitude of vector VL vector minus VC vector. So we can find tan phi as tan phi is equal to VL minus VC upon VR. On substituting the values, we write it as I naught XL minus I naught XC upon I naught R. I naught will be cancelled out, and tan phi is equal to XL minus XC upon R, or phi is equal to tan inverse XL minus XC upon R. This whole thing is for the case when XL is greater than XC or VL is greater than VC. Means this value is for XL greater than XC or VL greater than VC. If the case is like XL less than XC or VL less than VC, in that case the phasor diagram will be changed, and in the answers where we are getting XL minus XC, it will be XC minus XL. Similarly 10-5 will be XC minus XL upon R. So, the phasor diagram I am going to plot for this case also. So this will be the phasor diagram when VC is greater than VL. In that case the resultant we get will be VC minus VL, and it will be in the direction of VC vector, and VC and VL both are making pi by 2 with this direction of VR vector or I vector. The resultant is the diagonal of this parallelogram. If we use the parallelogram law of vector addition for VC vector minus VL vector and VR vector, then this diagonal is the resultant, which makes an angle omega t with the axis and phi with the current. So we have to find the magnitude for epsilon and current के साथ उसका direction, that is phi. So the only change that we get during the calculation is epsilon naught is equal to under root V naught R square plus, in first case it was V naught L minus V naught C. Here it is V naught C minus V naught L ka square, because the resultant is VC minus VL. So when we solve this, we get epsilon naught is equal to I naught under root R square plus XC minus XL ka whole square, and it gives I naught is equal to epsilon naught upon under root R square plus XC minus XL ka whole square. The effective resistance in this case is under root R square plus XC minus XL square, which implies impedance is under root R square plus XC minus XL square. So if we make an impedance triangle for it, it will be R, hypotenuse Z, and this axis, this length is XC minus XL. In case 1 it was XL minus XC, but here it is XC minus XL. Rest things are same. So this is the impedance triangle for this case. And for 10 phi, if we want to find 10 phi from this, so we get 10 phi is equal to XC minus XL upon R. XC minus XL upon R, or we can also find it from this phasor diagram, which shows that VC minus VL upon VR. Ultimately it gives us the answer XC minus XL upon R. So this answer is also changed. There it was XL minus XC. When XC is greater than XL or VC is greater than VL, it becomes XC minus XL upon R. After these two cases, there is one more case, the third case, where the two values are same. That means when XL is equal to XC or VL is equal to VC. In this case, phi is equal to 0 and the EMF and current will be in same phase, and at that time the LCR circuit is purely resistive, because there is no the reactances are equal, XL and XC, and they are opposite to each other. So in this case, series LCR circuit is purely resistive, and when it is purely resistive, we know that for a purely resistive circuit, the EMF and current, the EMF and the current will be in same phase. Okay, so this is the third case where XL is equal to XC or VL is equal to VC, and at that time phi is equal to 0. which means that the circuit is purely resistive and the current and EMF will be in same phase. This is the first part of this video. Second part will also be coming soon. So in this first part we studied about the LCR circuit. This is whole about the LCR circuit. In the second part of this video we will be studying about the resonance condition of a series LCR circuit. Means when it shows resonance, how it is possible, and what is its resonant frequency, what are the characteristics of a series resonant circuit, what is its sharpness, Q factor. So all these things we will compile in second part of this video. For that, stay tuned and keep studying. Thank you.